I got interested in this a few years ago when a colleague showed me patterns of wrinkles in carbon nanotubes. And these are tubes which are a billionth of a meter in diameter, or a few times that, and they're often essentially concentric. So you have one tube inside another one, inside another one. You can have as many as 50, 60 layers. And when you bend them, you see a pattern which you can actually see on a much larger scale with a thin sheet of rubber, which I have rolled up over here, in order to form a tube, but the tube itself is essentially got many, many layers. And when I bend that tube, you actually start to see the formation of wrinkles. And it may or may not be surprising that the same ideas that essentially explain what happens on the large scale in the rubber also explain what happens on the very, very small scale, almost a billion times smaller. And in fact, this occurs not only on the scale of a rubber tube, but occurs on the scale of an elephant's trunk, where you see similar patterns. Because an elephant's trunk has layers of muscles, and when the elephant tries to essentially bend its trunk, one layer slips somewhat compared to another one, and that causes these wrinkles to form. So the same ideas essentially carry over from something as small as a billionth of a meter to something as large as close to a meter, showing the unity that one can see when you use a little bit of geometry and a little bit of physics. In a map, it's very easy to unfold a map, but very difficult to refold a map, because every fold has two possibilities. It can either fold one way, like so, or it can fold the other way. Because every fold in one direction is perpendicular to a fold in another direction, and so these folds are independent of each other. How can you get around that? So a Japanese engineer 35 years ago, Koryo Miura, essentially discovered something that nature had known about for 300 million years. And that is that if you make the folds not at right angles to each other, but you make the folds at any angle except 90 degrees, in other words, this is the most degenerate situation, any other situation is better, then in fact all the folds get coupled to each other, as in this model of a hornbeam or a beech leaf, made in fact by a friend of mine, Biruta Kressling. And you can see that if I basically am able to, by pulling just at the base, I can open almost the entire leaf and I can close it. So that unlike in a map where every fold is independent of every other fold, here all the folds are coupled together. And we've been trying to understand how these kinds of folds arise spontaneously rather than in an engineering way by building it in one by one. And second, how do I optimize the angles so that I get properties that I want? For example, how quickly I can take it out in one direction, or how slowly, and so on and so forth.
Professor Lakshminarayana Mahadevan keeps props in his office to help visitors understand his work. This one is a toroidal bubble made of interlocked metal rings spinning around a central tube. He hopes to learn what limits the speed of its descent.
If I blow between the paper and the table very, very gently, you see that the paper rises a tiny bit and then is more or less stationary. It rises because the pressure associated with the flow of the fluid is just sufficient to lift the paper off, but the paper itself, as I said, doesn't oscillate. On the other hand, if I start to blow very hard, you start violent oscillation, and the violent oscillation also produces sound. And I'm studying this with colleagues here, with students and postdocs, in order to try and understand what the mechanisms are that are associated with how DC, in this case a continuous flow, is converted to AC, associated with vibrations, because it appears again on many different scales in many different problems. In fact, the reason you're able to hear me is because something similar is happening in my vocal folds. When I aspirate or when I breathe through them, the vocal folds start to oscillate, they create sound, and when I create the sound, I can use my mouth and my tongue to filter it. And I'll give you another example of that, which is associated with making the sound of a rolling R. So if I blow between my palate and my tongue gently, nothing happens. You can hear a whistle sometimes, but you don't hear a very strong oscillation. On the other hand, if I blow very, very rapidly, you can hear it. It's the same physics that's appearing there between my tongue and my palate, associated with the flow coupling to the elastic oscillations of the tongue, that appears here between the flow and the piece of paper.